Let's draw Lewis symbols for potassium and for chlorine. So let's see, let's pick a color. Blue. Blue would be good. So potassium has the element symbol K. How many valence electrons does potassium have? 1? Yes. There's a Lewis symbol for potassium. That's hard, huh? Chlorine. Cl. How many valence electrons does chlorine have? 7. So what we usually do when we're drawing the dots is we'll put one on the top, and you put one on each side before you start pairing them up. And I'll end up with 7. Now, if the unpaired electron is on the left or on the top or the right, it doesn't matter. It really just doesn't matter. But we want to be able to see how the electrons are paired up. There's actually some significance to that. So here's chlorine with 7 valence electrons. And what does it want? It wants one more electron, doesn't it? And here's potassium. Potassium has 1 valence electron. If potassium would give this electron to chlorine, then she would be really happy, right? She'd have her octet. But what would that do to potassium? Well, let's look. Here's potassium's electron configuration. There's the valence electron. If we peel that off, if we take this one off, what's left? Well, this is 0. Underneath, there is a full shell. Because this 4s no longer has any electrons in it, it's not the highest principal energy level anymore. 3 is, and 3 is full. So by losing that 1 electron, you peel off this partial layer, and underneath is this beautiful layer of onion electrons. So that's what happens. Potassium says, hey, I'll give you, oops, wrong thing. I'll give you my electron. And now I have a positive charge, but I have a full valence shell. We don't draw all those dots in the Lewis structures when we form a cation. We understand that underneath there is a full shell. And so if the metal gets rid of all of its valence electrons and we show it, it looks kind of naked there with no dots, but it's fine. Underneath it has a full suit of clothing. And then over here, this guy has gained an electron, and so it now has a charge. And we're going to put brackets around it because we don't want this minus sign to get lost among the dots. Now we have a positive ion and a negative ion, and suddenly they're very attracted to each other. And that forms an ionic bond. So use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. So magnesium is Mg. And how many valence electrons does magnesium have? 2. And nitrogen has how many? 5. 1, 2, 3, 4, 5. So this is where in chemistry land, see those noble gases? Those are like the cool kids. Have I talked to you about the cool kids? Okay, yeah. Those are the cool kids, and everybody wants to be like them, right? And the electrons are like your clothing. And so you can change your clothing. You can't change who you are. And so this nitrogen is like, man, if I could get 3 more electrons, I'd look like the in crowd, and I'd be good. I need my octet. And magnesium's thinking, I need to ditch these 2 extra electrons I have so that underneath I can show off, my cool threads or whatever. And so the magnesium says, well, sure, I'll give you 1 of my electrons. In fact, I'll give you 2 of my electrons. And so there's 1, there's 2. And the magnesium has lost those electrons. Now, the nitrogen has a 2- charge. and the magnesium has a 2 plus charge. Is everybody happy? No, magnesium is tickled. He's great. Nitrogen is like almost, just so close. I just need one more. Well, where there's one magnesium atom, there's probably another one. So enter magnesium atom number 2. And he's also looking to get rid of 2 electrons. And the nitrogen begs one off of him. So now this magnesium is +1. And the nitrogen is 3-. The nitrogen has arrived. What about this magnesium ion? Is he happy? No, he's not happy. It's so sad. Well, he needs to find someone to give that electron to. So we need another nitrogen. So magnesium says, hey, you need an electron here, take this one. And then he's thinking, phew, I feel so much better now. So magnesium 2 plus. All this color changing is going to make me dizzy or something. Now we have 2 happy magnesiums and 1 happy nitrogen and 1 unhappy nitrogen. What do we need? Another magnesium. You guys are smart. You see where this is going. There's another magnesium. So nitrogen begs 2 electrons off of that magnesium. Now this magnesium's a 2 plus charge, and this nitrogen is 3-. When we get 3 magnesium atoms and 2 nitrogen atoms together, they can transfer electrons in a way that they all end up with an octet. And so we look and we see this is going to be a ratio of 3 magnesiums to 2 nitrogens. And so the formula for that compound is Mg3N2. Which we learned to predict just from some rules we learned about the periodic table, but we didn't understand why. This is more why the ions form the way they do. Any questions? I think that's fun. I like that. Okay, lattice energy, the rest of the story. Oops. And okay, I'm just going to take that cord off because it keeps touching my computer. So when ionic compounds are formed, the formation of them is usually quite exothermic, meaning a lot of energy is given off. And if we just look at the ionization energies and the electron affinities of the metals and nonmetals involved, it doesn't add up. It just doesn't add up. So there's something called lattice energy. This is the energy that's associated with the formation of a crystalline lattice of alternating cations and anions. And when they quantify this, they measure it from gaseous ions. So it's the potential energy that's being lowered when opposite charges come together. The potential energy is lowered, that energy has to go somewhere, and it's released as heat energy. So magnetics. Have you guys played with magnetics? The little magnetic balls and sticks, and they click and they stick together, right? They want to get together. And that's what these ions are like. When they click together, they give off energy. And it's the lattice energy that causes them to form. So here we have an illustration. This looks like it's exploding, but it's coming together. All these sodium and chloride ions are attracting each other into a lattice of alternating positive and negative ions. And when those coalesce into a solid, you get a lot of heat being emitted. And that heat emitted is the lattice energy, and that can be measured. Which brings us to the Bornheimer Cycle. The Bornheimer Cycle is a hypothetical series of steps that helps us to represent the formation of an ionic compound from its constituent elements. And it's the easiest way to calculate lattice energies. And so we use Hess's law, and we're going to choose steps in which the delta H is known. We also need to know the overall change in enthalpy. And we can do this because these energies are state functions, right? And so how you formed the substance doesn't matter. It's just the difference in energy between before and after. And so we make up this hypothetical series of steps to form it so that we can add up things that we know to find the overall change. Formation, yeah, this is important because I often end up talking like this, but it's not true. Formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. That's not what makes it exothermic. It's exothermic because when those ions come together in a lattice, it releases a great deal of energy. So here is a Bornheimer cycle for the production of sodium chloride from sodium, the element in its solid state, and chlorine as an element in its gas state. The potential energy of the individual elements is higher than of the compound. Yeah. So down here is the sodium chloride solid. That's our product. And where are we starting? We're actually starting right here. Oh, she's a missionary. So here we've got, this is where we are. This is where we're starting from. Sodium, metal, chlorine gas. And we want to know the enthalpy change in the formation of sodium chloride from sodium and chlorine. And so we create this imaginary path. So we first take sodium metal and vaporize it. And that can be done. And so there's energy involved in that. And then we take the chlorine gas, the diatomic chlorine, and we make it chlorine atoms. And there's energy for that. And then we ionize those ions. First we ionize the sodium, and that requires some energy. And then we add an electron to chlorine. Remember, electron affinity for nonmetals is negative, and so that actually brings the energy down a little bit. And then we have this is the lattice energy. This is the formation from the ions in their gas states of the sodium chloride in the solid state. And so this is the lattice energy. So we can figure this out by adding all these other things together. There are trends in lattice energies. One thing that affects lattice energy is ion size. If we look at metal chlorides, here's lithium chloride, sodium chloride, potassium chloride, and cesium chloride. We see that the lattice energy is most negative for lithium chloride. And it decreases, getting closer to zero for cesium chloride. Why is this? Well, the lattice energy depends on how close the ions are in the lattice. Lithium ions are much smaller than cesium ions, and so the distance between the atoms between the ions is smaller. Here the distance is 241 picometers, here it's 348 picometers. Because remember from Coulombs Law, the energy is proportional to 1 over the distance between the charges. So if the charges are closer, then the energy is larger. Don't let the minus sign mess up your thinking. Okay, minus signs just, they're a bane of people's existence. It's just annoying minus signs. The minus means that this is going to be an exothermic process when this lattice forms. That's what the negative means. This is giving off more energy than this one because the lithium ion and the chloride ion are closer together than the cesium and the chloride ion. Does that make sense? I'm getting blank stares. Okay, I got some nods. We'll go on then. The ion charge also affects the lattice energy. Coulombs Law says energy is proportional to the product of the charges. If you've got +1 and -1, or +2 and -2, it's going to be a different amount of energy. The higher the charges, the more attraction there is. And so if we look at sodium fluoride and calcium oxide, the distances between the nuclei are very similar, 239 and 231 picometers. But the charges are different. This is +2, -2, and this is +1, -1. And so we see that the lattice energy for calcium oxide is 3,414 kilojoules per mole, and for sodium fluoride is only 910. So it depends on the charges as well. So lattice energies become less exothermic with increasing radius, and they become more exothermic with increasing magnitude of charge. I think the best way to remember stuff like this is just to remember Coulombs Law. So Coulombs Law says that the energy is proportional to Q1, Q2, it's a really bad 2, divided by R. So Q is the charge. Q is the charge. Q1, charge on one ion. Q2, charge on the other ion. If those are larger, the energy is larger. If the radius is smaller, the energy is larger because we're dividing by a smaller number. So, an example, arrange the following in order of increasing magnitude of lattice energy. We've got lithium bromide, potassium iodide, and calcium oxide. So we want to find the one with the smallest lattice energy first, and then go to larger lattice energy. Well, what are the differences in these guys? Are there charge differences? Yeah. So calcium and oxygen, this is a +2, -2 situation, right? Lithium bromide is a +1, -1, and potassium iodide is +1, -1. So here we've got 2 times 2 is 4, 1 times 1 is 1, 1 times 1 is 1. So this one, just based on charges, is going to be 4 times as large. So that's probably the biggest one. Difference in charge is going to have more effect than difference in radius. So we're going to put calcium oxide over here as the largest one. And then we have to choose between lithium bromide and potassium iodide. So we need to look at the periodic table. So lithium and potassium, which ion is larger? Potassium is larger. Okay, so this guy is bigger, and that guy is smaller. Comparing bromide and iodide, which one's bigger? The iodide is bigger, and the bromide is smaller. So this one is the largest ions. The charges between, we're just comparing these two right now. The charges on the ions are the same, but these are larger and these are smaller. Which one is going to have more attraction? The smaller ones. So the smaller one is in the middle, and the big one is at the bottom. Well, that's not what I meant to do. I need to get rid of that because I don't have room to write what I want to write. And Ki is here. Because when you have 2 big ions, this distance is large. When R is big, E is smaller. Okay? Any questions? No comments on my artwork. Models and reality. Does this bonding model explain the properties of ionic compounds? Well, we know that ionic compounds have high melting points. They are not conductive as solids, and they are conductive as solutions. Well, why don't they conduct as a solid? They're fixed in place by this huge lattice energy. They're just really held together. If we melt them or if we dissolve them in a solution, Now the ions are free to move, and it will conduct electricity. Any questions? The strength of the attraction also is why the melting point is so high. Ionic bonds are very, very strong. It's attraction between opposite charges.